Assalamu alaikum and hello to everyone. I hope you are doing very well. In this tutorial we are going to solve some numerical problems related with thermal expansion of matter. Let's do some revision first. According to Boyle's law, at constant temperature, pressure and volume of a gas are inversely proportional to each other, and mathematically we can, as you have seen before, we can write it like this: the product of pressure and volume is equal to constant, or we can say that the product of initial pressure and volume is equal to the product of final pressure and volume of a gas, and they remain constant. If they keep on changing, the product will remain constant. And the Charles law states that at constant pressure, the volume and temperature of a gas are directly proportional to each other, and mathematically we can write it like this: that the ratio of volume to temperature is a constant value, or we can say that the ratio of initial volume to initial temperature is equal to the ratio of final volume to final temperature, and these quantities or these ratios remain constant. For an the ideal gas law states that for an ideal gas, the pressure, volume, and temperature of a gas are related to each other with this mathematical relation: PV is equal to nRT. Here, P is the absolute pressure in pascals, V is the volume in cubic meters, and R is the gas constant, which value is 8.31 joules per mole per Kelvin. Okay, first problem, it is related with Boyle's law. It states that a rubber balloon is filled with helium gas at the pressure of 1.05 times 10 raised to the power minus 6 pascals and has a volume of 0.3 cubic meters. The balloon is then let off and raises up to a height where the pressure is 5.23 times 10 raised to the power 4 pascals. You know that when at height the pressure reduces, so at the near to the ground level or the near to the sea level, the pressure is higher. As we go up, the pressure reduces. So the balloon was going up initially. At its height, the pressure was it is supposed to be 10 raised to the power 6, not minus 6. It should be 6. Okay, so initially the initial pressure was 1.05 into 10 times 10 raised to the power 6 pascals, and when it goes to a certain height, the pressure reduces to 5.23 times 10 raised to the power 4 pascals. Now you have to estimate the size of the balloon at that height. Okay, size of the balloon means that the volume of it, assuming there is no change in temperature. So when there is no change in temperature, we apply Boyle's law. The given data is initial pressure is equal to 1.05 times 10 raised to the power 6 pascals, initial volume is 0.3 cubic meters, and final pressure is 10 raised to the power 4 pascals. And since we know that the gas inside the balloon has the same volume as the balloon, that's why we are going to calculate the volume, the final volume of the gas, which will reflect the size of the balloon itself. So size of the balloon at the height where pressure is P2 means at P2 pressure, the volume of the gas we need to find out, means we need to find V2. So we are going to use Boyle's law for that, which states that at a constant temperature, the product of pressure and volume is a constant quantity. So P1 V1 is equal to P2 V2, means the product of initial volume and pressure is equal to the product of final pressure and volume of the gas. Now from this formula, we will derive the value of V2 by rearranging the terms. So V2 is equal to P1 V1 over P2. Now we will insert the values and do calculations. After calculations, we get 0.603 cubic meters. So initially, when the pressure was high, the pressure was at 1.05 times 10 raised to the power 6. The volume of the balloon was 0.3 cubic meters, and when the pressure reduces to 5.23 times 10 raised to the power 4 pascals, the volume of the balloon increases to 0.603 cubic meters. This is another example for Boyle's law. This example states that a gas of volume 5 decimeter cube or 5 cubic decimeter. You must remain careful with the units. Okay, a gas of volume 5 decimeter cube exerts a pressure of 2.02 times 10 raised to the power 5 kilopascals. This gas is completely pumped into another tank where it exerts a pressure of 1.01 times 10 raised to the power 5 kilopascals at the same temperature. Means the temperature is not changing, temperature is constant. We have to calculate the volume of that tank. The given data is initial volume, which is 2.02 times 10 raised to the power 5 kilopascals. Initial volume V1 is equal to 5 cubic decimeters. Final pressure is P2, which is equal to 1.01 times 10 raised to the power 5 kilopascals, and it is given that temperature is constant. And when the temperature is constant, we know which law to apply, that is Boyle's law. Okay, and we have to find out the volume of the tank, because the gas will acquire the volume of the volume of the tank, means that both will have same volume. We are going to calculate volume of that gas, which will reflect the volume of tank. Since you know that in this example the temperature remains constant, and Boyle's law states that for a constant temperature, the product of pressure and volume of a gas is a constant quantity. Or we can write it like this, that P1 times V1 is equal to P2 times V2. From here we can derive the value for V2. Then we insert values of P1, V1 and P2. Now we calculate and get our answer as 10 cubic decimeters. We can convert it into cubic centimeters also. We know that 1 decimeter is equal to 10 centimeters, and from here you can convert cubic decimeters to cubic centimeters. Problem number 3, this is related with Charles' law. This is a very short, simple problem. It says that find the initial volume of a gas at 150 kelvins if the final volume is 6 liters at 100 Kelvin. So in the previous examples you have calculated the final volumes. Here you have to calculate initial volume of a gas at a certain temperature, which is 150 K or 150 Kelvin, if the final volume is 6 liters at 100 Kelvin. Now you can see the temperature is changing, means you cannot apply Boyle's law. What is not changing? That is pressure. Okay, so in this case you can apply Charles' law. So in the given data we can note the values of initial temperature 150 Kelvin, final volume 6 liters, and final temperature which is 100 Kelvin. So one temperature is changed from 150 to 100, means that temperature is reduced. So if we are going to calculate initial volume, we have to consider, means if we want to know what the result should be, means the initial volume should be greater or the smaller we should have some idea from the change in the parameters. If the temperature is increasing, means the volume should increase. If the temperature is decreasing, the corresponding volume should decrease as well. Okay, we have to find out initial volume of the gas. So initially the temperature was high, right? So the volume must be large. Okay, the solution according to Charles' law, V over T is actually a constant value, and we can write V1 over T1 is equal to V2 over T2. From here we can derive the value of V1 by rearranging the terms like this. V1 is equal to V2 over T2 times T1. Now we simply insert values. V2, the final volume was 6 liters and final temperature is 100 Kelvin, while the initial temperature was 150 Kelvin. Now by doing the calculations, we get our volume as 9 liters. Problem number 4. This is also related with Charles' law. So a gas occupies a volume of 400 centimeters cube at 0 degrees Celsius and 780 millimeters of mercury. What volume will it occupy at 80 degrees Celsius and 780 millimeters of mercury? Express answer in liters also, means you have to convert units as well. In the problem, the units of volume are cubic centimeters, but once you have calculated, you have to convert centimeter cube into liters also. The given data is initial temperature, which is 0 degrees Celsius, and in order to convert it into Kelvin, we have to add 273 in the Celsius value. This is a very simple conversion. And initial volume of the gas is 400 cubic centimeters. Initial pressure is 780 millimeters of mercury. Final temperature is 80 degrees Celsius. We have to convert it into Kelvin because here we use the units Kelvin in all these laws. Final pressure is equal to 700 millimeters of mercury. You notice that initial and final pressures are same. There is no change, means pressure is constant. And which law is under the condition of constant pressure? That is Charles' law. And we have to find out the final volume of the gas, V2. We know that according to Charles' law, V1 over T1 is equal to V2 over T2, and from here we can derive the value of V2 like this. Now we simply insert the given values in the formula and perform necessary calculations. Our volume is 517.22 cubic centimeters. Now since you are asked to convert it into or express your answer in liters also, you have to convert it into liters. How you can do it? We know that 1 liter is equal to 1000 cubic centimeters. So you know how to convert units, we have already learned it. So therefore V2 is equal to 517.22 times 10 raised to the power minus 3 liters, and we get 0.517 liters. Sorry, it should have been V2. Okay, this is the last problem. In this problem, an ideal gas at 20 degrees Celsius and a pressure of 1.5 times 10 to the 5 pascals is in a container having a volume of 1 times 10 raised to the power minus 3 cubic meters. Determine the number of moles of a gas in the container when R is 8.31 joules per mole per Kelvin. This is the gas constant. Here from the units of the constant of this constant value can guide you which units you must use the quantities in the given statement. If there are some different units of the quantities, you have to convert. For example, in terms of temperature, it is given in centigrades, you have to convert in kelvins, because our constant, the one that we are using here, is represented in terms of Kelvin. Okay, the given data is temperature 20 degrees Celsius, pressure 1.5 times 10 raised to the power 5 pascals, volume is 1 times 10 raised to the power minus 3 cubic meters, and the gas constant is 8.31 joules per mole per Kelvin, and we have to find out number of moles of the gas in that container, which is represented with N. So we know that according to ideal gas law, PV is equal to nRT. We can solve this equation for N, and N will be equal to P times V divided by R times T. Insert values here, and we get our answer, which is 6.16 times 10 raised to the power minus 2 moles. That's all. And if you have any questions, you do not understand something, or if there is a confusion in anything, you can contact me. Thank you very much.